Okay, so now I'm going to walk you through the structure of the atom. So, as we said in previous conversation, an atom is the smallest piece of any element. It's the smallest particle of an element that retains the characteristics of the element, okay? So aluminum foil, here's a picture here, contains atoms of aluminum, right? So if we could get really, really small, obviously very, very small, this is just a cartoon picture of it, but you might see something that looked like a bunch of spheres that are arranged in sort of a three-dimensional array. This would be an atom of aluminum. Here's another atom of aluminum. Here's another atom of aluminum. Okay? So the learning goal then for this section is to describe the electrical charge of a proton, describe the charge of a proton, neutron, and electron, and identify their location within the atom. So we have a relatively modest learning goal, but I want to give you a little more of the history of the structure of the atom to help set it up. Okay, so again, our goal is to really identify the charges and where the locations of the particles in an atom. All right, so let's first of all start out with John Dalton. So John Dalton, wow, I think this was in the 1800s. I'm sorry to say I've even forgotten when it is. But John Dalton's atomic theory contains 4 points. Number 1, matter is made up of tiny particles, okay? And they're called atoms, right? And the atoms of an element are similar to each other, but different from those of other elements. And then 2 or more elements combine, atoms of 2 or more elements combine to make compounds, and they can be rearranged to form new combinations in something called a chemical reaction. Now, in a chemical reaction, atoms are never created or destroyed, okay? And this was John Dalton. And first of all, they're tiny particles of matter. They're similar within elements, they're different between elements, and they can be rearranged in a chemical reaction. So, the electrical charges in an atom, it's important to appreciate that we have protons, which have a positive charge, electrons, which have a negative charge, and neutrons, which have no charge at all. We know that positive charges repel each other, and negative charges repel each other, but unlike charges attract, right? So a negative and a positive are going to come together. Right? Like charges repel and unlike charges attract. So the second stage after John Dalton of the discovery of the atom was J.J. Thompson. So J.J. Thompson, from his experiment, J.J. Thompson realized that cathode rays contain negatively charged particles. Cathode rays contain negatively charged particles, and so he said, wait, if we have rays that contain negatively charged particles, maybe we've got particles in an atom, and we're going to call those electrons. Okay, so that was J.J. Thompson. That's to credit to J.J. Thompson. So J.J. Thompson then proposed a model called the plum pudding model of an atom. The plum pudding model of an atom says that protons and electrons were randomly distributed throughout an atom in something that he envisioned to be like plum pudding. So here's a negatively charged electron, and the positively charged pudding is the other stuff. Okay, so that was his model. Now we know that that's not correct anymore, thanks to Ernest Rutherford, who I believe did his work at Oberlin College in Ohio. In Rutherford's gold foil experiment, that may be wrong. So someone's going to come in the comments and say what a bonehead I am for not knowing, but I frankly don't really care that much. So Rutherford, anyway, gold foil experiment. This is really cool. What he did was he took some gold atoms, a gold foil, and he shot positively charged particles at it. Okay, mostly they went straight through the atoms. Some of them were ricocheted off like billiard balls, right? Deflected off only occasionally. Rutherford's experiment concluded that there must be a small, dense, positively charged nucleus that deflects positive charged particles that come close to its center. So here's sort of a layout of what he did. He's got a sort of a detector around the edge, okay? Here's a gold foil right there. Can you see the gold foil? Super thin gold sheet, basically just an array of atoms. Now here's a side shot of the gold foil right here. Here's the gold atoms. And as he was shooting, he took this little lead container and a source of particles. They were alpha particles. Lead container, which has a little hole right there. And so the particles come out there, okay? Try to do a straight line. particles come out here, right, and go through the gold foil. Most of them go straight through, and then they're just detected in the back of this detector. Some of them, however, bounce off and go off to the side, or even bounce back and come over here, right? So here's another picture of that. You have an alpha particle coming through, and if this is mostly space, it's just going to go straight through, right? And most of them did. But occasionally, your alpha particle, which is a positively charged particle, would come here, and bam, it will hit the nucleus and bounce off. Okay? That's what that's about. So, the structure of an atom then, after Rutherford's experiment, was pretty well resolved. That we have a nucleus located at the center of the atom that's mostly made up of positive particles and, well, not mostly, entirely made up of positive particles and neutral particles called neutrons. All right? And that's where most of the mass comes of the atom, because those are huge. All right? Compared to the electrons, which are tiny. Right? So protons and neutrons are in the nucleus, and then there's a cloud around on the outside of the nucleus that is made up of electrons, all right, which are very, very small, and it's basically empty space. The electrons are moving super, super fast. They're very small. So the electron cloud outside the nucleus really is very much like an empty space. So here's another picture of that. Sorry for the emails coming in. All right, so let's take lithium metal. You've seen this picture before. It's in your textbook. And if you take that lithium metal and you look at it really, really closely, you might find that you had a bunch of lithium atoms, right? There's a lithium atom. Here's a lithium atom. Here's a lithium. These are just cartoons, right? But you can imagine that they might be arrayed in sort of a three-dimensional array like that, little lithium atoms, okay? Now let's look at one of those atoms. If we took one of those atoms and blew it up, we would find that there's a little tiny nucleus here that's made up of protons and neutrons, and outside the nucleus is an electron cloud that's made up of electrons, okay? All right, so more details on that. Because the mass of subatomic particles are so small, chemists use, instead of measuring them in kilograms or grams, we use a very small unit called the atomic mass unit. Okay, one atomic mass unit is defined as 1/12 of the mass of a carbon-12 atom, which has 6 protons and 6 neutrons. So each proton and neutron is about 1 AMU. It's about 1 atomic mass unit. And by the way, 1 AMU is about 1.6 times 10 to the, not 1.6, 1.9, I think. You know, I don't remember. 1 point something, who cares? 1 point something times 10 to the minus 29 kilograms. 27. Man, this is terrible. 1 times 10 to the minus 27 kilograms. It's a lot smaller, right? That's times 10 to the minus 27 kilograms. So that's why we need a unit that's so small, right? 1 AMU, by the way, biologists don't call it an AMU. They call it a Dalton, which is named after John Dalton. I'm not sure why biologists do that. Biologists are pretty much crazy. All right, so, but electrons, oh, that's what atomic mass units are, the protons and neutrons, but electrons are so small that we usually don't even include them in the mass of the atom. They're just tiny. They're 1/2000th the size of a proton or neutron. So let's look at that in particular, okay? Here's the symbol of a proton, simply P or P plus, okay? It has a charge of +1. The charge, I remember, this is 1.6 times 10 to the minus 19 coulombs, okay? And that's, but we're going to call that a +1. That's +1, okay? We'll just call it +1 charge on a neutron. Its mass is 1.007 AMU. It's about 1 AMU. And its nucleus, it's located in the nucleus of the atom. A neutron, its symbol is N0. It has a charge of 0, right? And its mass is about the same as a proton. It's about 1 AMU, and it's found in the nucleus. An electron, here's where things get screwy. E minus is the symbol, as a -1 charge, same as this charge, but the opposite in sign of a proton, but it's way smaller. Look at how much smaller it is in atomic mass units. It's about 1/2000th the size, and it's found in its own area outside the nucleus. Okay, so let's do this knowledge check. Pause the video, do this knowledge check, and come back on and see, and compare your answers to mine. Okay, let me suppose you paused it. Which of the following subatomic particles fits each of the descriptions below? Found outside the nucleus. Found outside the nucleus. That would be electrons. Have a positive charge. That would be protons. And have a mass but no charge. And that would be neutrons. All right, so hopefully that's a brief enough introduction to the atom. That's just about all we're going to need, so I don't want to go any further than that. Hope it's good.